Hello, everyone. Well, I hope you're enjoying the symposium so far. My name is Gabriel Matsumoto. I'm a first-year PhD student here at the University of Florida and the current treasurer of the Plant Science Council. I believe I speak for all the students and everyone here in this symposium that we're excited and honored to hear from our last speaker today, Dr. David Bubeck, who is the current research director in seed product development for Corteva Agrisciences. Dave Bubeck grew on a diverse crop and livestock farm near Clarion, Iowa. Dave earned his bachelor degree in agronomy and his master's of science degree in plant breeding and cytogenetics from Iowa State University. Then, he received his PhD in plant breeding and crop science at the North Carolina State University. In his current role, Dr. Bubeck oversees global parent characterization, global germplasm security, as well as providing support for multiple regulatory compliance stewardship aspects for the Corteva Plant Breeding Organization. Dave also is currently the past president of the National Association of Plant Breeders, or NAPB. He serves on the board of the Seed Science Foundation for the American Seed Trade Association as the chair, the research chair, and he serves on the board of director for Living History Farms. We are really grateful to have you here. Thank you so much for your time, Dr. Bubeck. And without further ado, I'll give you the word.
Very good. Thank you, Gabriel. And thanks to the whole Plant Science Council too. I was able to join for a good part of the day, not the entire morning, but you guys have done a great job planning a conference and excellent work and an excellent experience for all of you. And I've looked at some of your past work too. So my compliments to your efforts at University of Florida, and you guys have done a really great job with the Plant Science Symposia of the past as well. So thank you for that. Really pleased today to be here for Corteva as one of the sponsors and to give a bit of a private sector view on what I believe is a very timely core topic, for center point for the conference, that breeding for climate change and a stress resilient agriculture. And I want to give you a number of different perspectives on this as we close down this portion of the conference today. I have been a research director since 2000, and so everything I'm going to talk about today, I'm going to acknowledge others, and I'm not going to give a long list of names of the past and present Corteva and legacy pioneer folks that have had an impact on my thinking on this, but there have been a lot of people, and I haven't run a personally active research program since I've been a research director for 22 years. So I'm really relying on others and hopefully influencing others in a positive way in terms of this whole plant breeding endeavor. And so the seed product development group that I'm in as a research director is our entire global plant breeding organization titled Seed Product Development. And so that's where I came from. And I decided to title this Plant Breeding to Enable Sustainable Production Agriculture. I think goes along right with your theme of the conference this week. So I'm going to kind of talk into 4 different categories, or sort of my agenda for today. I'm going to talk just briefly about our Corteva mission and sustainability commitment. Fits right in with your conference theme. And then I'll talk about plant breeding and how it drives resilience. Talk about plant breeding and some of its limitations towards sustainability and what some of the limitations of the future might be. And then finally, I'm going to end with hopefully some thought-provoking aspects of future technology usage towards plant breeding and crop improvement, with a bit of a focus on genome editing and the future potentials of genome editing, as well as some aspects of global policy. So that's where we're going for today. And I really think that the fundamental mission statement of Corteva also fits in so well with this theme. And one of the reasons that I really enjoy being part of Corteva Agriscience is this very mission statement to enrich the lives of those who produce, as well as those who consume, and for generations to come. So the generations to come part really speaks to that sustainability in agriculture We are very much a row crop, field crop company in the 11 different species that we breed in. We don't have vegetables. We're really the typical traditional field crops. You see cotton and wheat in the picture there that I chose, but we're very much a field crop oriented company. A couple of years ago, a lot of the private sector in agriculture has been compelled to make some sustainability statements. Production agriculture gets criticized a lot for not being sustainable, maybe not being very environmentally attentive, and so a lot of the companies have put forth sustainability statements, and I want to make sure that as we work through the sustainability statement that we identify the areas that plant breeding really has the opportunity to contribute to greatly. And I think I bolded a couple here on decreasing the greenhouse gas emissions while increasing yields. We are all about genetic gain for grain yields and protecting that genetic gain by reducing and paying attention to abiotic and biotic stresses that reduce plant productivity. And so that's a big one for us. And we need to, and I'll speak more about that as I go through the talk as well. And then also enhancing biodiversity on 10 million hectares is what the claim was here. And I think taking things out of a monocrop situation by increasing the yield and intensity, the input and output value of a given cropping unit land area enables that biodiversity to occur on other arable acres around the world. And so I think that's another key one that plant breeding directly contributes to. So those are our commitments to sustainability. You can find those out on our website. To zero in a little bit more specifically on Corteva's mission on sustainability, and we brought up the point that we are one of the largest farmers in the world. When you look at our seed production globally, as well as the research ground that we do research plots on, and a lot of those are conducted on both land that Corteva owns, as well as our research cooperators, our farmer cooperators. And we have a lot of influence on how those acres are managed. All those acres are managed under some kind of a contract. And so you see on the left there, you have the research centers in the middle. That's where I sit. And then we have our seed production group where we do handoffs of our parent seed to our breeder seed, let's say, to our supply organization as they produce the product. They're producing that product on farmer acres too. And that direct influence on those customers, we can have a very positive influence on production practices and maintaining acres using the best and most sustainable practices possible. So a lot of influence there. That ends up being on more than 2 million acres globally that we have that very significant sphere of influence. And so you can see some of the very specific things we're doing. We're doing grower education. We're establishing partnerships with growers and the agricultural community. We're using nitrogen stabilizers. Corn gets a lot of criticism for nitrogen utilization. We're trying to utilize that as efficiently and effectively as possible, and we're trying to manage the best agronomy on those acres. And so one of the things on our seed production acres for corn that we have a perfect opportunity to do is really drive a cover crop system. And so really protecting those acres for 12 months of the year, even during the non-growing season. So really important for us. So that's a bit on Corteva's mission and sustainability. Now we'll move over to, I want to dive into several aspects of how I believe plant breeding drives resilience and agricultural sustainability ultimately. And I'll go through several examples of this. With the majority of my career being in corn breeding background, you'll see that most of my examples that I'll share will be related to corn as a species, but certainly extended to other crops. One of the things that that was started at Pioneer Hybrid, one of the heritage companies of Corteva, was the ERA study. And this was actually started many years ago, back in the kind of conception in the 60s and then really started in the 70s to look at the decades of introduction, commercialization of corn hybrids. And based on the decade of release, we have our germplasm that goes back all the way to the beginnings of Pioneer Hybrid in 1926. And so we have these decades of release of these hybrids that go through the 20s, 30s, 40s, 50s, and on forward to today. And one of the things that the decade study has demonstrated is that the bushels per acre that are produced per inch of water in drought environments, and how the decades have really improved in that efficiency of water use to produce the same bushel per inch of water that's available during that corn production year. So really outstanding all the way through the 90s, and some really good data that represents that. And a lot of that data is published. And so if you can look up authors, Charlie Messina has been on some of those. Don Duvick was on a lot of those early papers. Mark Cooper was on some of the more recent papers. So the whole plethora of authors on those papers, really instrumental. A more recent one, and Charlie Messina, now at University of Florida, is also on this paper. And Christine mentioned Charlie during her talk as well. We're already missing Charlie at Corteva, so I hope you guys are treating him well at the University of Florida in his early days there. And I'm sure he'll do a great job on faculty there at Florida. But this is a paper right out of Charlie, and this, really further documents how genetic gain is integrated and predicting improvements in crop productivity. And so this is another way to look at the year of commercial release and how that grain yield has gone up. And this is a chart that's right out of this publication. And then again, how evapotranspiration has changed over the decades, and how grain yield has increased with less moisture required per unit of grain that's been produced. So a really good paper on that to further establish what we knew through the decade or era studies. And another interesting way to look at this is that this is all based off of USDA statistics on corn production in the U.S. And a couple things I want to point out here. If you look at the single cross era of hybrids that have been produced, and you go from about 1997 and forward, there's a pretty good decline in the variance off of this trend line. So you have the slope of 1.88, but you can see we've post GMOs, we have in fact stabilized the yield, even though climate variance from year to year seems to continue to increase. The stabilization and the variance off of that line relative to the previous years seems to have declined to some extent. I haven't tried to quantify it here, but it is evidenced. So on-farm performance, a few things here: year over year consistency, what's happening across environments, what are the agronomic flaws, how are we dealing with water stress tolerance, and you can find the drought years, they're still evident. So I think this was the drought year of 2012, very significant and widespread drought. So you still have variance off that line, but given the significance of that drought, the variance is probably quite a bit less than it would have been if we wouldn't have been breeding for stress tolerance for all those years. Another thing I want to point out is notice the slope of these are the National Corn Growers Association contests and the top winners, the first place winners from 1983 to 2020. And I think it's interesting to note that the slope of that line is quite a bit greater, more than twice as much greater as the slope of the average yields across all farms across the U.S. And I think that's an interesting testament to the whole goal of the contest entries from these farmers entering the National Corn Growers Contest is to eliminate as many of the biotic and abiotic pressures and stresses on corn production as possible. And so I think when you do that, it further identifies that we really have been maximizing all the things that contribute to top end yield potential. And so really, putting all the things into the products that enable that top end yield potential to be realized. And I think what we can do, and Christine did a nice job going through crop growth models and how they relate to whole genome prediction and whole genome selection in a breeding program. And I'll touch on that a little bit later, but only briefly. But I think it's interesting to think about how combining all of this into let's say a very holistic whole plant biology perspective and whole crop management perspective, what can we learn from the elimination of these biotic and abiotic pressures that would contribute and actually raise the slope of this entire trend line for corn production? So I think that's an interesting picture. And another way to look at how the impact of continuous corn improvement, not just breeding, but improved management practices, improved farmer practices, improved understanding of our growing environments, is if you take this baseline of 2021 and say, okay, it took exactly in 2021 this many acres, was 85.1 million acres, and these are US numbers, took 85.1 million acres to produce that much total corn production. And then if you go back from 2021 as ground zero, let's say, and say how many acres would it have taken in a given decade, so you can see the x-axis here goes from 2011, 2001, decreasing by 10 years each bar. And you can see how many acres that it would have taken back in 1921 and 1931 to produce the 2021 crop. And so very much a testament to, if we wouldn't have done continuous genetic gain or management practice improvement in corn production in the US, there's no way we could have produced the 2021 crop, because there's simply not that much arable land back in the, let's say, the pre-1960s. So a really nice way, I think, to look at the overall sustainability of what we've contributed through both the public and the private sectors working together on corn improvement. Okay, so now I want to shift a little bit gears to the actual breeding pipeline, and we often talk about our germplasm pool, and that is the pool of individuals of corn inbreds that are available globally, because we do have a global germplasm base. So those are available globally to contribute to breeding programs that are active around the world. And we do very much have a one corn breeding view. All of our corn breeders around the world, and actually all of our plant breeders across crops, are very well connected. We live more than ever in an interconnected world where we can connect virtually, just like we are here today, and also use the best practices as far as breeding methodologies, of software that's available for us to incorporate into our breeding programs and our knowledge base. And so the germplasm pool is the entire collection of what's available to a breeder, individual breeder, to breed with. And so creating those populations and those initial breeding crosses, and then evaluating those crosses, and then selecting how do we go out to the field and select those crosses. And then it all gets recycled and added to an ever increasing germplasm pool. And so that kind of goes full cycle, and then it just goes around that circle. And so I have what I call an inbred development cycle, and you could kind of think of that top row of things, of activities going on, as your inbred development cycle, which we try to turn that crank really fast, and the faster that we can go relative to our competition, might add to if our rate of genetic gain could be better for yield and traits of interest than our competitors, then we'll put out a very, very highly competitive product in the marketplace. The other genetic gain cycle to look at is in the case of a hybrid crop like corn, is the product development cycle for hybrids. And so you're creating the hybrids for testing on the top end of this cycle. You're putting lots and lots of new genetic combinations together, and you're selecting those through multiple years of testing, all the way till you get to commercial release. And at the beginning, you know a lot about the genotype, but you might not know very much yet about the phenotype. And so you're increasing your knowledge of the phenotype as you go down through that funnel. One of the consequences then, as you look at the right-hand side here, one of the consequences of that is hopefully over time in breeding cycles, you're getting realized genetic gain, albeit you have enough positive genetic variants to achieve that genetic gain. But one of the consequences is you're decreasing genetic diversity. And so how do you continue to make genetic gain? At some point, do you reach a plateau or a problem in the amount of genetic diversity that you actually have as that declines, as you select for what is you think is the best and discard what you think is the worst? And so we have to think of ways to antagonize that over our breeding cycles. Okay, so we've been using doubled haploids here in this whole machine. I find it fascinating that the ability to bring the genotype together and with doubled haploids. So we fill the front end of our pipeline with a very high percentage of doubled haploid derived lines. So right away at the beginning, that gives you a fixed genotype that's never going to change again, and the ability to have that genotype right at the beginning and be able to do molecular marker fingerprint on that genotype right at the beginning enables the whole process. And so being able to do whole genome prediction at every stage of everything that we're doing and enhance that, the ability to select for the phenotype because you're adding the genotypic knowledge is tremendous. And this is a slide that came out of some of the work that a number of our researchers did. That was a very, very large group of populations and over multiple years, where we were really trying to model how good our prediction systems were really performing, and also inform future methods of how we really needed to drive estimation sets and predictions. And so, but having the doubled haploids available really enabled, and it was a perfect marriage in the early 2000s to bring the ability to do molecular markers at really high and dense genotyping, and know exactly where your recombinations were, and be able to inform every stage of our testing as you go from that top-down funnel of advancement. And so leveraging doubled haploids in this beautiful marriage of doubled haploids and more cost-effective genotyping was a wonderful journey. So another way to look at this, and Tom Tang, who was in Charlie Messina's group just before Charlie left Corteva, and Tom's in good hands, Charlie, so not to fear. I know you are aware that he's carrying on the work. I like the way he laid this out into four kind of aspects. And one, of course, is the phenotype. And how do we do a better job all the time of predicting the phenotype and estimating the phenotype? Our ability to do that only comes through our ability to have that genotypic knowledge once again. And so it's that combination of the observed phenotypes, and the more accurate that we can observe those phenotypes, the better quality data in the field, using spatial designs, picking the best locations for testing, achieving uniform data, and then having good quality marker data with no errors on SNP data that goes with that, really enables that genotypic model, which enables our whole genome prediction system. And so anyway, that really important second part. So the phenotype together with the genotype, and then together with the environment. And so this is where you get into a little bit of the question of how do we think about environments in an ever-changing climate, whether it be incremental changes or more significant variation from year to year. And I think the ability to put together the phenotypes over years with the marker data and thinking about environmental classification aspects of weather and soil data and other environmental factors. How do we put all these things together to ultimately begin to drive that biological model and really thinking about the whole plant, whole environment system, and including the management systems that go with that. So I talked a little bit about the journey that we've been on for fingerprinting and being able to do high density fingerprinting. We've been on a more difficult journey over the course of my now almost 32 years in the industry, that it's been a difficult journey getting phenotyping down to a more cost-effective level. So an amazing drop, more than 1,000-fold drop during the course of my career, during the course of the last 20 years, actually, in the cost of genotyping as we moved to a SNP model. And yet the phenotype is very costly to get. So the more that we can build together, and this is about all I'm going to say on crop growth models and coming together with whole genome prediction, because Christine covered it very well, but bringing those two things together to inform future breeding programs, I think, is really going to be instrumental. And and the big question there really becomes what's different about what we're going to select in terms of product that goes to our customers, and until the crop growth models really inform those breeding programs to advance potentially type 2 errors where we've dropped something in our pipeline because we thought it wasn't as good as what we're actually selling, but in fact it's better. So that's your basic type 2 statistical error and very fundamental principle in the pipeline of advancing products in our pipeline. And so this is kind of bringing it all together. This was a slide that Radu Totur recently used at the American Seed Trade meetings in Chicago, but I like the way it brought kind of encapsulated a lot of this into one picture of creating those selection candidates. That's really leveraging that germplasm base. We talk a lot about right sizing the pools of those populations. How many recombinants of a highly likely to succeed breeding cross? What's the right size of those pools? And how do we begin to better predict what the right size of those pools are? Genome feature extraction, phenome feature extraction, just another way to be thinking about this process flow, and to making sure all of that is driving towards whatever breeding objectives that you've got set up specifically for the region that you're breeding in. And actually that all comes first. I might slide that over to the left-hand side, and you have to have those breeding objectives by traits firmly established before you ever start. And then that decision data delivery to the breeder, how that's packaged, what it looks like, how a breeder can inform those decisions, what machine learning and artificial intelligence goes into that, and that the breeder can quickly turn around those data decisions into advancement, because the breeder is working 12 months of the year, advancing things, leveraging off-season nurseries in the wintertime. So that timely decision data delivery is really, really critical to the whole thing. Okay, so now I want to talk briefly about some of the limitations that I think we are seeing in the current plant breeding model, and just touch on a few of these. And as a bit of a point of diversion, and this goes back to the whole climate change, resilient agriculture concept here, but and again, this is purely a maize picture on this slide, but across the seed industry, we have now commercialized, this number is not quite correct. We've commercialized about 21 industry events since 1996. So we're running a little bit less than one single transgenic event per year. Now, and one of the reasons that I wanted to point this slide out is we've taken care of insects pretty well. So lots of different events for Lepidopteran targeted insects, a few less events for Coleopteran, corn rootworm type insects, and then a little bit for herbicides and one or two agronomic things that are out there, and then an output trait known to impact amylase. And I purposely left off a couple that are less important to the grower as input traits, but they may be important to the company as producibility traits for, you know, sterility and seed production or things like that. But my point on this is, even with GMO technology, we have limited ourselves to just a few categories of impact. And there have been some attempts made on drought resistance, which have been marginal, I would say, in value on drought resistance. And I would say actually that whole genome selection and native selection for native genes in drought resistance has actually been more effective than some of the transgenic approaches. And so I think when it comes to climate change and making plant breeding promises, we have to be a little bit careful about what we can do within native genomes about not over-promising too much. And yet, on the other hand, breeding by the very nature of breeding and selecting and advancing in a given year does enable some buffering against those trends in climate change. So I want to have a balanced view there. Another limitation that I see in breeding is genetic diversity. And I mentioned this in one of my earlier slides, but genetic diversity trends over time are really something to watch out for, something the breeding community needs to think of as a way to, we know that selecting for the best things, the best performing entities, regardless of what trait you're selecting for, we know that we are gonna screen out some genetic diversity in doing that. And the more intense and rigorous our selections, and the greater your selection intensity, the faster that genetic diversity will decline. And so we monitor this regularly in each of our groups of smaller breeders. We call those evaluation zones. So within those, we do breeding project reviews. I get very involved as a research director in helping conduct those breeding project reviews and assessing what are we doing over time. And genetic diversity is one of those things that we watch over time. You know, some very basic fundamental genetic diversity measures such as co-ancestry coefficients, and monitoring how those change over a period of time. And then effective population sizes, that other kinds of measures of genetic diversity, and watching those decline. And what do we do within a individual breeding group to try to antagonize those declines, and also learning over time, how much genetic diversity do we need to sustain a targeted genetic gain for yield? And the plasticity of the genome in maize and other crops has continued to amaze me. And there's some really good examples of that with, Illinois high oil, low oil, high protein, low protein selection in a recurrent selection kind of format that have demonstrated that plasticity of the genome. So it's not a simple answer how much genetic diversity is really needed. Okay. One of the other challenges to a breeder is just the number of traits that could be under selection under a particular moment in time or a cycle of breeding. And it's a massively long list of traits. And so it really becomes important that within a geography that you become very specific about that breeding program model and what you actually need to select for. Because you can't actually select for everything and make progress on all things. So that's a real challenge to the breeding community. So I think I'm putting this as a challenge, but it's also an opportunity in breeding is how do we bring all of this complexity together and bring into the G by E by M model and really advance And it kind of goes back to the other comment that I was making. Very complex models, a lot of details, but until it really starts to change what we select and advance in products, it's interesting, and certainly from an academic standpoint, it's interesting, but it has limited value unless, sorry, I had a pop up. Sorry. And until we really refine the model and how it would impact in advance, it will continue to have kind of limited value in our breeding model. So, and I'm going to skip past that one in the essence of time here, because I want to make sure I leave enough time for questions. And I want to talk about genome editing a little bit and jumping gears to the fourth topic. And so genome editing, I think, and I want to make sure that I touch on global policies around genome editing too, in this one. So we have an example that's coming through our pipeline right now. We have been actively selecting for a very important trait, northern corn leaf blight. Northern corn leaf blight is not only important in the United States, but in many of the countries around the world. And across many latitudes, from the northern temperate latitudes all the way into the tropical latitudes, northern leaf blight has found its home and is a significant challenge. It's a foliar blight, and reduces that photosynthetic capacity and potential. And so we can move multiple genes around. We know what the resistance genes are. We can leverage genome editing. We can consider co-locating those native genes with other genes. And I think it's an interesting concept to whether we could produce through genome editing a durable enough solution for a trait like northern corn leaf blight that the breeders would no longer actually have to put that into their selection intensity when they select in advance, and that long list of traits. And so as a concept here, what if the breeders could eliminate from that long list of maize traits that I showed, what if they could eliminate 3 or 4 or 5 disease traits all at once? Or what if they could solve standability and stock quality issues, or remove multiple stock rotting organisms to strengthen the stock strength of plants? And that breeders could actually take those traits off of their selection criteria, as long as you could create a durable enough solution through genome editing. I think it makes for an interesting question. So this is an active project that we have, and we're looking at other CRISPR approaches for other disease traits as well, not just in corn, but other crops as well. So that's that one. And I put together, what is, when you think about genome editing and future potential, what if we could go beyond what is currently possible with current plant breeding science and technology? And so thinking about, this was a paper that was published and had some co-authorship with Corteva folks. But what if we could do chromosomal rearrangements and potentially change the phenotypes and further unlock genetic variation, and use genome editing approaches to do that? I think one of the limitations that I mentioned, deciding what the population size should be, how many doubled haploid derived lines do you need from a given population? Well, what if we could do effectively control genomic recombination elements and control those, and maybe leverage genome editing as a tool to increase genomic recombination where we wanted it to occur and decrease it where we don't want it to occur, and had more significant control. So that could potentially change the number of recombinants that we need from a given cross. What if we could maximize identification of gene expression for loci that have become fixed during the breeding process, and leverage approaches to further improve phenotypic response? And so that's another one. We've talked a little bit about using genome editing to develop hybridization systems for crops that are biologically, they're currently self-pollinated. But what if you could create heterotic patterns and create hybrid vigor through a system that was created from genome editing? So that's another one, provocative, I would say, for the future. Enabling co-location of native traits, unleashing major portions of the genome for improved maintenance of genetic diversity and additional trait selection. And so what if we could co-locate genes and entirely here I'm talking about native genes thus far. I'm not talking about a GMO approach, but in fact, just native traits. Reduce or eliminate certain traits during plant breeding selection via genome editing only solution. And then this one, I know some people think this is really a stretch, but when we think about regulatory control of native promoters, what if we could enable highly qualitative and infinitesimally small gene effect to be expressed as larger, and I meant to say highly quantitative, sorry, not qualitative, highly quantitative, infinitesimal genes to express larger and more measurable effect. And that really gets into this next one as well. This is kind of a long-term dream that I have from a genetic diversity sympathizer perspective of how could we better utilize, genome collections, national plant germplasm system and other collections that contain unadapted materials, even all the way to wild relatives, and utilize those. So the last point, none of this is going to work unless we can, more effectively advocate for global acceptance of technologies like genome editing. And I do have some concerns that our current global approach to regulatory is going to have an effect on paralyzing our ability to get to the next generations of genome editing. And I think that is a risk that we have with a lot of technologies applied to plant breeding and crop improvement, that there is a risk that we get stuck in both policy acceptance and social acceptance of some of these technologies. So we really have to drive, and I challenge the students that are on to be thinking about, there is a place for all of you, and some of you in particular, to really be advocates of technologies that can really improve the science of crop improvement. Whether it's a field crop or a vegetable, I think it's a really important direction. And a lot of that will, determine whether genome editing resides on this chart in 2070. Right now we've got it on here. We think about all the different technologies that have contributed to plant breeding and crop improvement over the years. I'm not sure yet, whether genome editing will be on here as we look out over the next 30, 40, 50 years. So your careers will help drive whether that is an effective way that we can contribute to crop improvement or not, and ultimately to climate change, resilience, and sustainability of agriculture. So with that, I want to stop. I used a little more time than I had planned. I'm going to give one last advertisement. Since I am the past president of National Association of Plant Breeders, you are all welcome to come to, we are planning a live event for the next NAPB conference. Iowa State University will be the host of that in August of this year. We hope we can have it live, and that's what we're planning for at this present time. And so I hope to see at least some of you there. And I plan to be there myself. It's just down the road from me in central Iowa, so it's very easy. But anyway, thank you for your time and attention. I'll take any questions you have.
Hey, thank you very much, Dr. Bubeck, for your presentation. It was really good. It put so many different topics and aspects of plant breeding in perspective for us, for the new generation, the upcoming generation. Thank you very much. It was a really interesting talk. We do have some questions here. I'll read them out for you. So the first one is, could you please give an example of how Corteva would antagonize the decrease in diversity while maintaining genetic gain?
Yeah, that was a setup for that question. Thank you for asking it, whoever asked it. There is no simple answer to this. And, I think I alluded to that we are globally connected. So we have all our breeding programs connected around the world. We have our germplasm therefore connected around the world. And so germplasm within a species is flowing around the world. A lot invested in corn, and leveraging and knowledge and leveraging that germplasm around the world. So the way I think of genetic diversity, you have your concentric rings of, let's say, genetic diversity. Think of it as concentric rings and spheres. You have what you would most naturally be choosing that is highly adapted to your individual geography. So if you're sitting in Indiana and your responsibility is to breed for Indiana, Ohio, maybe Illinois, you're gonna look first in that concentric inner circle at the germplasm that is most predictive to perform in your region. And then you have full knowledge of the genome. So you know what chromosomal regions that suffer from narrowness, and you also know the trait correlations of those chromosomal regions. So rather than just a random, let's go all the way to to maize germplasm collections and National Plant Germplasm System, you say, where do I have to go look for both trait diversity as well as genomic diversity, and where is the most likely place to succeed that goes outside beyond my initial inner circle of breeding targets that I might go after. And so you look to your neighbors east and west of you and north and south of you. And then you look further and further around the world as things become, potentially more concerning on the genetic diversity front. There may be, and I hope there will be cases in the future where we see particular genetic vulnerabilities of disease susceptibility, where because we have knowledge of a full global germplasm base for a given crop species, that we know where to go solve the genetic vulnerability. And I think that's the ultimate endpoint to live in a post-genomic era where we know all the germplasm that's available to us. Now an even bigger question is, can we leverage some future generation of genome editing that we actually create the variation that we need for a given trait? And do we have the ability to create genetic diversity that is needed to improve crop performance? So that's the ultimate vision I'd like to lay out for the students as you think about your whole career. I don't think that last part's going to happen in my career, but I do think there's a possibility of it happening in yours.
Thank you very much. There is a question that kind of goes along the same lines that we're discussing right now. So in terms of maintaining genetic diversity in the breeding population, how do you decide on which new genotypes to introduce, especially for yield-related traits? Can it be argued that breeding for disease resistance traits introduce enough diversity in the germplasm?
Yeah, another great question. So you have, as I mentioned, with estimation sets and prediction systems, and you have the genotype of everything in hand. So you have the ability to leverage genomic prediction at every stage of decision making. So even at the point where you're creating populations and you're selecting which populations to create in the first place, and then which ones to use and how deeply to sample those populations, you have the full array of genotypic knowledge in front of you. And so you also have the full array of diversity knowledge in front of you, and predictions for traits beyond yield. And so traits that are of interest, like I mentioned northern leaf blight for genome editing as an example. If you have to still apply selection pressure for northern leaf blight, you want to make sure that you're not just focusing on the yield predictor as the single trait. And so You have to, it's tricky, but you just have to maintain some balance. But you are correct that if you go down the narrow path of only selecting for yield, you will absolutely get what you select for. And so agronomic difficulties are most certain to come if you only pay attention to yield. And genetic narrowness comes really quickly with it too. So you have to look at it broadly.
Thank you very much. There are a couple questions also kind of like in the scenario of looking at the future and plant breeding in the future. One of those is Corteva looking to evaluate and incorporate new crops as potential food sources, even like for a specific region or just in general?
Yeah, we're right at the moment, we're always entertaining the idea of expanding the species that we work with. We have a group that we call Farming Solutions and Digital, looking at different cropping rotation systems. One thing that gets a lot of scrutiny, in my title slide, I only showed 2 crop species, corn and soybeans. And I did that for purpose because that is the dominant rotation system across the Corn Belt in the U.S. And I do think when I grew up on a farm in the 60s and 70s in north central Iowa, and we had corn, soybeans, oats, alfalfa, not really any wheat, generally speaking. Before my time, there was a fiber crop known as hemp that was grown during World War II on the farm that I grew up on. But let's just say a much more diverse cropping system than what most Corn Belt farmers have today. It's corn and soy. I do think there's great opportunity as we look forward to greatly increasing the diversity of that cropping system. And I think we're going to go, the likely trend will be going away from a more monocropping or dual cropping system to a more complex system in the future. And I think that's going to be good for biodiversity and good for the environment and good for soil health. I think it has a lot of really good aspects. We're also looking at what we do with cover crops. And the trick about cover crops is we don't have enough growing season in the Midwest following full season crops like corn and soybeans. Once you get above the say about the 42nd latitude, north latitude 42, you really have trouble getting enough season to grow much of a secondary, for the purpose of a cover crop. But we are looking at cover crop systems as well and where they fit into our whole seeds portfolio. So that's another example.
Good. Thank you very much. Josh, do we still have some time? There are 2 more questions that I have in here.
Yeah. Ask the questions as long as Dave has time.
I'm good.
Are we good? Okay, cool. Thank you. Okay, so another one of the questions about this perspective for the scenario in 2050 is, in your opinion, what is expected from the next generation of plant scientists in this 2050 scenario?
Being much smarter than I was. Okay, so I'll give an example. When I started in the industry in 91, I started in April of 91. I didn't have any appreciation that society and policy agencies would care about regulating any aspect of the seed industry. And I would say that across vegetables and field crops and flowers, almost anything. About the only regulatory aspect when I started, food safety was, of course, always been concerned about. food safety from a perspective of bacterial, E. coli and salmonella and food poisoning, things like that. And so about the only kind of restriction or regulation applied were related to phytosanitary issues, which relate to food safety. It relates to seed movement around the world. How do we move healthy and safe food and seed around the world? To avoid pandemics occurring in the seed industry is really an important issue for us. So that's been around for, ever since the seed business became multinational and was, moving seed around the world. We were largely unregulated besides that until GMOs came around. And, the regulatory system that was built in the 90s on GMOs was relatively new. And I was not well informed about how much scrutiny that would receive around the world and how much variance there would be from one country to the next on how to treat GMOs. In spite of our now 25-year history of GMO use and tremendously safe history of GMO use, our regulatory path and timeline has not gotten any shorter. In fact, it's only gotten longer. And so when I made that point about being an advocate for technology and the safe use of those technologies, and in one of my last slides there, it really is something that the future generation of scientists, how do you communicate better with what's your elevator speech for GMOs? What's your elevator speech for breeding safety? And I mean, the history of plant breeding has a tremendous history of safe use. And we may need to publish more on that. What I hate to see happen as you think out to 2050 in the next many decades coming for you folks is that technology growth and turning multiple generations of technology over, that it doesn't get paralyzed. And so how do you do that? I think there's going to have to be a better connection between the public and private sector, but also between the consumer and the social acceptance is going to be just as important as the policy acceptance.
Okay, thank you very much. I think you also ended up answering the other question,
Okay.
which was about how do you see the future and market of gene-edited crops. So I think you touched base a little bit on that as well. I mean, do you want to add anything else to this question?
Yeah, the only thing I would add on gene edited right now is you have to think about, I'm gonna pick on grain crops. They're traded around the world. And so when you think about corn grain going around the world, you have to make sure whatever grain you're moving, whatever seed you're selling, whatever hybrids you're selling, are approved in the markets where, in the export markets where you're cultivating that crop. And so the world has to get better aligned on genome editing. So there's some really heavy lifting to be done on that before the pathway is clear. And for vegetables, it's a little bit maybe more clear, but look at your fresh supermarket produce, both fruits and vegetables. They are moving. They don't all come from the United States, and vice versa. So even on fruits and vegetables, we're going to have to clear the way for a better aligned system of approving these kind of traits. Hey, thanks all you guys for what you do. I may try to join you a little bit tomorrow as well if my schedule allows. But really good conference. Thanks for inviting me.
Thank you very much for your presentation. Sorry, I had a little trouble here with my microphone. I was not able to mute it right away. But once again, thank you very much for all the insights and for bringing all these great topics for discussion. This was our last presentation of today. Now I'll hand the word to Josh, our president again of the Plant Science Council, for some closing remarks. And yeah, thank you very much once again, Dr. Bubeck.